Welcome to Leader IAS and Yashas Institute Navi Mumbai. Myself Professor Suhas Sargar. These are the self-explanatory audio video book for the self-study of a student. In this video, we are going to learn and understand State Board of Maharashtra Standard 10th English Medium Subject Science and Technology Part 1 Chapter number 1 Gravitation. What we are going to learn in this topic: first, gravitation; second, Kepler's law; third, circular motion and centripetal force; Newton's universal law of gravitation; acceleration due to gravitational force of the earth; freefall and escape velocity. So let's begin. Can you recall what are the effects of a force acting on an object? What type of the forces are you familiar with? What do you know about the gravitational force? We have seen in the previous standard that the gravitational force is a universal force and it acts not only between two objects on the earth but also between any two objects in the universe. Let us now learn how this force was discovered. First, gravitation. As we have learned, the phenomenon of a gravitation was discovered by Sir Isaac Newton. As the story goes, he discovered the force by seeing an apple fall from a tree on the ground. He wondered why all apples fall vertically downward and not an angle to the vertical. Why do they fall? Why they do not fly up in a horizontal direction? Question mark. After much thought, he came to the conclusion that the earth must be attracting the apple towards itself, and this attractive force must be directed towards the center of the earth. The direction from the apple on the tree to the center of the earth is a vertical direction at the position of the apple, and thus the apple falls vertically downward. In figure 1.1, see the concept of the gravitational force and the gravitational force between the earth and the moon. See in the picture, there is a moon, there is a earth, and there is a gravitational force acting between them. You are seeing a tree. Below the tree, the Newton is sitting and the process of falling apple. In the figure 1.1, on the left shows an apple tree on the earth. The force on an apple on the tree is toward the center of the earth, that is, along the perpendicular from the position of the apple to the surface of the earth. The figure also shows the gravitational force between the earth and the moon. The distance in the figure are not according to scale. Newton thought that if the force of gravitation acts on apples on a tree at a different height from the surface of the earth, can it also act on objects at even greater heights, much farther away from the earth, like for example the moon? Question mark. Can it act on even farther objects like the other planets and sun? Question mark. In box, use of ICT means information communication technology. Collect the videos and PPTs about the gravitational force of different planets. Box close. Force and motion. We have seen that a force is necessary to change the speed as well as the direction of motion of an object. Can you recall what are Newton's law of motion? Question mark. In a box, see the Sir Isaac Newton's photo. Introduction to scientist. The great scientist Sir Isaac Newton was one of the greatest scientists of recent time. He was born in England. He gave his laws of motion, equation of motion, and the theory of gravity in his book Principia. Before this book was written, Kepler had given the three laws describing the planetary motion. However, the reason why the planet moved in the way described by Kepler's law was not known. Newton, with his theory of gravity, mathematically derived a Kepler's law. In addition to these, the Newton did ground-breaking work in several areas including light, heat, and sound, as well as mathematics. He invented a new branch of mathematics, and this is called calculus, and has a wide-ranging application in physics and mathematics. He was the first scientist to construct a reflecting telescope. Box closed. Next topic is circular motion and centripetal force. Dear listeners, these are the self-explanatory audio-video books which is very much helpful for the self-study of the student from Leader IAS and Yashas Institute, Navi Mumbai, Maharashtra. Myself, Professor Suhas Sargar. Next topic is a circular motion and centripetal force. Try this. Tie a stone to one end of a string. Take the other end in your hand and rotate the string so that the stone moves along a circle as shown in the figure 1.2. Are you applying any force on the stone? Question mark. See in the figure A and the B. 1.2 figure, a stone tied to a string moving along a circular path and its velocity in a tangential direction. Try this. Tie a stone to one end of a string. Take the other end in your hand and rotate the string so that the stone moves along a circle as shown in a figure 1.2a. Are you applying any force on the stone? Question mark. In which direction is this force acting? Question mark. How will you stop this force from acting? Question mark. What will be the effect on the stone? Question mark. As long as we are holding the string, we are pulling the stone towards us, that is, towards the center of the circle, and are applying a force towards it. The force stops acting if you release the string. In this case, the stone will fly off along a straight line, which is the tangent to the circle at the position of the stone when the string is released, because that is the direction of its velocity at that instant of time. See in the figure 1.2 diagram B. You may recall that we have performed a similar activity previously in which a 5 rupee coin kept on rotating circular disc flies off the desk along the tangent to this disc. Thus, a force acts on any object moving along a circle and it is directed towards the center of the circle. This is called the centripetal force. Centripetal means center seeking, that is, object trying to go towards the center of the circle because of this force. You know that the moon, which is a natural satellite of the earth, goes around it in a definite orbit. The direction of motion of the moon as well as its speed constantly changes during this motion. Do you think some forces is constantly acting on the moon? Question mark. What must be the direction of these forces? Question mark. How would its motion have been if no such force acted on it? Question mark. Do the other planet in the solar system revolve around the sun in a similar fashion? Question mark. Is similar force acting on them? Question mark. What must be its direction? Question mark. From the above activity, example and a question, it is clear that for the moon to go around the earth, there must be a force which is exerted on the moon, and this force acting must be exerted by the earth, which attracts the moon towards itself. Similarly, the sun must be attracting the planets, including the earth, towards itself. Dear listeners, these are the self-explanatory audio video book podcast from Leader IAS and Yashas Institute, Navi Mumbai, Maharashtra. Myself, Professor Suhas Sargar. The next topic, the Kepler's Law. Planetary motion had been observed by astronomers since ancient times. Before Galileo, all observation of the planet's position were made with the naked eyes. By the 16th century, a lot of data were available about planetary position and motion. Johannes Kepler studied these data. He noticed that the motion of the planet follows a certain law. He stated 3 laws describing the planetary motion. These are known as the Kepler's Law, which are given below. See in a box, do you know? Figure 1.3 and ellipse. An ellipse is a curve obtained by a cone is cut by an inclined plane. It has 2 focal points. The sum of the distances to the 2 focal points from every point on the curve is a constant. F1 and F2 are 2 focal points of the ellipse shown in a figure 1.3. If A, B and C are 3 points on the ellipse, then AF1 plus AF2 is equal to BF1 plus BF2 is equal to CF1 plus CF2. Box closed. Kepler's first law. In quote, the orbit of a planet is an ellipse with the sun at one of the foci. I repeat, the orbit of a planet is an ellipse with the sun at one of the foci. Figure 1.4. See it in the picture, the orbit of a planet moving around the sun. Figure 1.4 shows the elliptical orbit of a planet revolving around the sun. The position of the sun is indicated by capital S in the diagram. See it in the pictures or the diagram. Now the second Kepler's law or the Kepler's second law. The line joining the planet and the sun sweeps equal area in an equal interval of time. I repeat, the line joining the planet and the sun sweeps equal areas in equal intervals of time. AB and CD are the distances covered by the planet in equal time. That is, after equal intervals of time, the position of the planet starting from A and C are shown by B and D respectively. The straight lines A, S and C, S sweeps equal area in an equal interval of time. That is, area A, S, B and C, S, D are equal. Now next, the Kepler's third law. The square of its period of revolution around the sun is directly proportional to the cube of the mean distance of a planet from the sun. I repeat, square of its period of revolution around the sun is directly proportional to the cube of the mean distance of a planet from the sun. Thus, if the r is the average distance of the planet from the sun and t is the period of the revolutionary, then the t square is a proportional to r cube. That is, t square upon r cube is equal to constant is equal to k. Equation number 1. Kepler obtained these laws simply from the study of position of the planet obtained by regular observation. He had no explanation as to why a planet obeyed these laws. We will see below how these laws helped the Newton in the formulation of his theory of gravitation. Use your brain power. If the area ESF in a figure 1.4 is equal to area ASB, what you will infer by EF? Question mark. Newton's universal law of gravitation. The next topic is Newton's universal law of gravitation. All the above consideration, including the Kepler's law, led the Newton to formulate his theory of universal gravity. According to this theory, every object in the universe attracts every other object with a definite force. This force is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. Box. In a box, an introduction to scientists. Johannes Kepler, from 1571 to 1630, was a German astronomer and mathematician. He started working as a helper to the famous astronomer Tycho Brahe in Prague in the 1600th century. After the sudden death of Brahe in 1601, the Kepler was appointed as a royal mathematician in his place. Kepler used the observation of the planetary position made by Brahe to discover the laws of planetary motion. He wrote several books from his work was later used by Newton in postulating in his laws of gravitation. Figure 1.5. Gravitational force between two objects. See the force. Figure 1.5 shows that the two objects with the masses m1 and m2 kept at a distance d from each other. See in a picture. Mathematically, the gravitational force of attraction between these two bodies can be written as F is a proportional to m1 m2 upon e square, or F is equal to capital G into m1 m2 upon d square, equation number 2. Here the capital G is a constant of proportionality and is called the universal gravitational constant. The above law means that if the mass of one object is double, the force between the two objects is also double. Also, if the distance is double, the force decreases by a factor of 4. If the two bodies are spherical, the direction of a force is always along the line joining the center of the two bodies, and the distance between the centers is taken to be small d. In case when the bodies are not spherical or have irregular shape, then the direction of a force is along the line joining their centers of mass, and small d is taken to be at the distance between the two centers of mass. From equation second, it can be seen that the value of small g is the gravitational force acting between two unit masses kept at a unit distance away from each other. Thus, in a SI unit, the value of small g is equal to the gravitational force between two masses of 1 kg kept 1 meter apart. In box, use your brain power. Show that in a SI unit, the unit of G is a Newton meter square per kg square. The value of capital G was first experimentally measured by Henry Cavendish. In the SI unit, its value is 6.673 into 10 raised to minus 11 Newton meter square per kg square. Box closed. In another box, the center of mass of an object is the point inside or outside the object at which the total mass of the object can be assumed to be concentrated. The center of a mass of a spherical object having uniform density is at its geographical center. The center of mass of any object having uniform density is at its centroid. Box closed. Why did the Newton assume inverse square dependence on distance in his law of gravitation? He was helped by the Kepler's third law in this as shown below. Next topic, uniform circular motion or magnitude of centripetal force. Consider an object moving in a circle with a constant speed. We have seen earlier that such a motion is possible only when the object is constantly acted upon by a force directed towards the center of the circle. This force is called the centripetal force. If small m is the mass of the object, small v is its speed, and small r is the radius of the circle, then it can be shown that this force is equal to capital F is equal to mv square upon small r. If a planet is revolving around the sun, in a circular orbit in uniform circular motion, then the centripetal force acting on the planet towards the sun must be F is equal to mv square upon r, where m is the mass of the planet, v is its speed, and r is its distance from the sun. In a box, speed is equal to distance traveled upon time taken. Box closed. The speed of the planet can be expressed in its terms of the period of revolution, capital T, as follows. The distance traveled by planet in a one revolution is equal to perimeter of the orbit, that is 2 pi r. Distance of the planet from the sun is small r. Time taken or period of revolution is capital T. Now in the mathematical sum, small v is equal to distance travelled upon time taken. Means v is equal to 2 pi r upon capital T. Next, capital T, capital F is equal to mv square upon r, means F is equal to m in bracket 2 pi r upon T, the whole square upon small r, is equal to 4m pi square r upon T square. Now, multiplying and dividing by the r square, we get capital F is equal to 4m pi square upon r square into, in a bracket, r cube upon T square, bracket close. See in a picture, these are the equations. Now, according to the Kepler's third law, capital T square upon small r cube is equal to k constant. So, capital F is equal to 4m pi square upon r square capital K, but 4m pi square upon K is equal to constant. So now F is equal to constant into 1 upon r square. Therefore, capital F is proportion 1 upon r square. Thus, the Newton concluded that the centripetal force, which is the force acting on the planet and is responsible for its circular motion, must be inversely proportional to the square of the distance between the planet and the sun. Newton identified these forces with the force of gravity and hence postulated the inverse square law of gravitation. The gravitational force is much weaker than other forces in the nature, but it controls the universe and decides its future. This is possible because of the huge masses of the planet, stars, and other constitute the universe. Now in a box, use your brain power. Is there a gravitational force between the two objects kept on a table or between you and your friends sitting next to you? Question mark. If yes, why don't the two move towards each other? There are the few examples. Mathematical calculations are there. You can see in these pictures as well as in your hard or the soft copy of this book. So now in a box, do you know? You must be knowing about the high and the low tides that occur regularly in the sea. The level of a sea water at any given location along seashore increases and decreases twice a day at a regular intervals. High and low tides occur at different times at different places. The level of water in the sea changes because of the gravitational force exerted by the moon. Water directly under the moon gets pulled towards the moon, and the level of water there goes up, causing high tide at that place. At two places on the earth at a 90-degree from the place of high tide, the level of water is minimum and the low tide occurs there as shown in the figure 1.6. Low and high tides. In a box, collect the information about the high and low tides from geography books. Observe the timing of high and low tides at one place. When you go for a picnic to be a beach, take pictures and hold an exhibition. Box closed. Earth gravitational force. Will the velocity of a stone thrown vertically upward remain constant, or will it change with the time? Question mark. How will it change? Question mark. Why does not the stone moves up all the times? Why does it fall down after reaching a certain height? Question mark. What does its maximum height depend on? Question mark. The earth attracts very objects near it towards earth attracts every object near it towards itself because of the gravitational force. The center of a mass of the earth is situated at its center. So, the gravitational force on any object due to the earth is always directed towards the center of the earth. Because of this force, an object falls vertically downward on the earth. Similarly, when we throw a stone vertically upward, this force tries to pull it down and reduce its velocity. Due to this constant downward pull, the velocity becomes zero after a while. The pull continues to be exerted and the stone starts moving vertically downward towards the center of the earth under its influence. Use your brain power in a box. According to the Newton's law of gravitation, every object attracts every other object. Thus, if the earth attracts an apple towards itself, the apple also attracts the earth towards itself, the same force. Why then does the apple fall towards the earth, but the earth does not move towards the apple? Question mark. The gravitational force due to the earth also acts on the moon, because of which it revolves around the earth. Similar situation exists for the artificial satellite orbiting the earth. The moon and the artificial satellites orbit the earth. The earth attracts them towards itself, but unlike the falling apple, they do not fall on the earth. Why? This is because of the velocity of the moon and the satellite along their orbit. If this velocity was not there, they would have fallen on the earth. These are the podcast, audio video book, self-explanatory from the Leader IAS and Yashas Institute, Navi Mumbai. Myself, Professor Suhas Sargar. Now, in next topic, the Earth's gravitational acceleration. The Earth exerts gravitational force on objects near it. According to Newton's second law of motion, a force acting on a body results in its acceleration. Thus, The gravitational force due to the Earth on a body results in its acceleration. This is called acceleration due to gravity and denoted by small g. Acceleration is a vector, as the gravitational force on any object due to Earth is directed towards the center of the Earth. The direction of the acceleration due to gravity is also directed towards the center of the Earth, that is, vertically downwards. Think about it. First, what would happen if there were no gravity? Question. Second, what would happen if the value of the g was twice as large? There are some mathematical value of a small g on the surface of the Earth. See it in a picture. Can you tell in box what would be the value of a small g on the surface of the Earth if its mass was twice as large and its radius half of what it is now? Topic next. Variations in a value of small g. Change along the surface of the Earth. Will the value of small g be the same everywhere on the surface of the Earth? Question. The answer is no. The reason is that the shape of the Earth is not exactly spherical, and so the distance of a point on the surface of the Earth from its center differs somewhat from place to the place. Due to its rotation, the Earth bulges at the equator and is flatter at the poles. Its radius is the largest at the equator and smallest at the poles. The value of small g is thus highest, that is 9.832 meter per second square at the poles, and decreases with a decreasing latitude. It is the lowest 9.78 meter per second square at the equator. B. The change with the height. As we go above the Earth's surface, the value of small r in equation 5 increases and the value of small g decreases. However, the decrease is rather small for height, which are small in a comparison to Earth's radius. For example, remember that the radius of the Earth is 6,400 km. If an aeroplane is flying at a height of 10 km above the surface of the Earth, its distance from the Earth's surface changes from 6,400 km to 6,410 km. And the change in the value of the small g due to it is negligible. On the other hand, when we consider an artificial satellite orbiting the Earth, we have to take into account the change in the value of small g due to the large change in the distance of a satellite from center of the Earth. Some typical height and the values of these height are given in the following table. See these pictures. Table showing changes in a small g with a height above the Earth's surface. See, next topic is the change with the depth. The value of the small g also changes if you go inside the Earth. The value of small r in equation 5 decreases, and one would think that the value of the small g should increases as per the formula. However, the part of the Earth which contributes toward the gravitational force felt by the object also decreases, which means that the value of small m to be used in equation 5 also decreases. As a combined result of change in small r and capital M, the value of small g decreases as we go deep inside the Earth. Think about it. Will the direction of the gravitational force change as we go inside the Earth? What will be the value of small g at the center of the Earth? Question mark. Every planet and the satellite has a different mass and radius. Hence, according to equation 6, the values of small g on their surface are different. On the moon, it is about the 1 by 6th of the value of the Earth. As a result, using the same amount of force, we can jump 6 times higher on the moon as compared to that on the Earth. Mass and object. Next topic is a mass and weight. Mass and weight. First, mass. Mass is the amount of matter present in the object. Repeat. Mass is the amount of matter present in the object. The SI unit of mass is a kg. Mass is a scalar quantity. Its value is the same everywhere. Its value does not change even when we go to another planet. According to Newton's first law, it is the measure of the inertia of an object. Higher the mass, higher is the inertia. Next topic is a weight. The weight of an object is defined as a force with which the object attracts the object. I repeat, the weight of an object is defined as a force with which the Earth attracts the object. Earth attracts the object. The force capital F on object of a mass small m on the Earth on the surface of the Earth can be written in equation 4. Therefore, the weight W is equal to capital F is equal to small mg. Here, the small g is equal to capital G capital M upon capital R square. Box close. Weight being a force, its SI unit is a Newton. Also, the weight being a force is a vector quantity and its direction is towards the center of the Earth. As the value of the g is not same everywhere, the weight of an object changes from place to place. So, its mass is a constant everywhere. In a box, colloquially, they use weight for the mass and weight and measure the weight in a kilogram, which is the unit of mass. But in a scientific language, when we say that Raju's weight is 75 kg, we are talking about the Raju's mass. What we mean is the Raju's weight is equal to the gravitational force on 75 kg mass. As the Raju's mass is 75 kg, his weight on the Earth, his F is equal to mg is equal to 75 into 9.8 means 735 Newton. The weight of mass, 1 kg mass, the weight of 1 kg mass is 1 into 9.8 is equal to 9.8 Newton. Our weighing machine tells us the mass. The two scale balance is a shops compare two weights, that is two masses. Box closed. Use your brain power. Will your weight remain constant as you go above the surface of the Earth? Question mark. Second question. Suppose you are standing on a tall ladder. If your distance from the center of the Earth is a capital 2r, what will be your weight? There is some example you see in your soft or the hard copy book. Now in next topic, in a box, do you know the gravitational waves? The waves are created on the surface of water when we drop a stone into it. Similarly, you must have seen the waves generated on a string when both its ends are held in a hand and it is shaken. Light is also a type of waves called electromagnetic waves. Gamma rays, X-rays, ultraviolet rays, infrared rays, microwave and radio waves are all different types of electromagnetic waves. Astronomical objects emit these waves and we receive them using our instrument. All our knowledge about the universe has been obtained through these waves. Gravitational waves are very different types of waves. They have been called the waves on the fabric of space-time. Einstein predicted their existence in 1960. These waves are very weak and it is very difficult to detect them. Scientists have constructed extremely sensitive instruments to detect the gravitational waves emitted by astronomical sources. Among these, laser interferometric gravitational wave observatory, that is LIGO, is the prominent one. Exactly after 100 years of their prediction, scientists detected these waves coming from astronomical source. Indian scientists have contributed significantly in this discovery. This discovery has opened a new path to obtain information about the universe. Box closed. These are the self-explanatory podcast of audio video book from Leader IAS and Yashas Institute, Navi Mumbai, Maharashtra. Myself, Professor Suhas Sargar. These podcasts are supportive for the self-study of a student. Next topic is a free fall. Take a small stone, hold it in your hand. Which forces are acting on the stone? Now release the stone. What do you observe? Question mark. What are the forces acting on the stone after you release it? Question mark. We know that the force of gravity due to the earth acts on each and every object. When we were holding the stone in our hand, the stone was experiencing this force, but it was balanced by a force that we were applying on it in the opposite direction. As a result, the stone remained at a rest. Once we release the stone from our hands, the only force that acts on it is the gravitational force of the earth, and the stone falls down under its influence. Whenever an object moves under the influence of the force of gravity alone, it is said to be falling freely. Thus, the released stone is in the free fall. In a free fall, the initial velocity of the object is zero and goes on increasing due to the acceleration due to gravity of the earth. During free fall, the frictional force due to air opposes the motion of the object, and a buoyant force also acts on the object. Thus, true free fall is possible only in a vacuum. For a freely falling object, the velocity on reaching the earth and the time taken for it can be calculated by using Newton's equation of motion. For free fall, the initial velocity small u is equal to 0 and the acceleration a is equal to small g. Thus we can write the equation as, see it in a box, small v is equal to small gt, small s is equal to 1 by 2 gt square, small v square is equal to 2 ds. For calculating the motion of an object towards thrown upwards, acceleration is a negative, that is in a direction opposite to the velocity, and is taken to be small g. The magnitude of small g is the same, but the velocity of the object decreases because of these small v acceleration. The moon and the artificial satellites are moving only under influence of the gravitational field of the earth. Thus they are in a free fall. In a box, do you know the value of small g is the same for all objects at a given place on the earth. Thus, any two objects, irrespective of their masses or any other properties, when dropped from the same height and falling freely, will reach the earth at the same time. Galileo is said to have performed an experiment around 1590 in the Italian city of Pisa. He dropped two spheres of different masses from the leaning tower of Pisa to demonstrate that both spheres reached the ground at the same time. When we drop a feather and a heavy stone at the same time from a height, they do not reach the earth at the same time. The feather experiences a buoyant force and a frictional force due to air and therefore floats and reaches the ground slowly. Later than the heavy stone, the buoyant and the frictional force on the stone are much less than the weight of the stone and does not affect the speed of the stone much. Recently, the scientists performed these experiments in a vacuum and showed that the feather and the stone indeed reach the earth at the same time. Box closed. See, there are some solved examples based on the theory in your soft copy PDF or in hard copy. These are the self-explanatory podcast of the audio video book from Leader IAS and Yashas Institute, Navi Mumbai, Maharashtra. Myself, Professor Suhas Sargar. The next topic is a gravitational potential energy. We have studied the potential energy in the last standard. The energy stored in an object because of its position or a state is called the potential energy. This energy is a relative and increases as we go to a greater height from the surface of the earth. We had assumed that the potential energy of an object of a mass m at a height h from the ground is a small mgh, and on the ground it is 0. When small h is small compared to the radius capital R of the earth, we can assume small g to be constant and can use the above formula in bracket mgh. But for a large value of h, the value of small g decreases with increase in a small h. For an object at infinite distance from the earth, the value of small g is 0 and the earth's gravitational force does not act on the object. So it is more appropriate to assume the value of potential energy to be 0 there. Thus, for smaller distances, that is height, the potential energy is less than 0. That is, it is negative. When an object is at a height small h from the surface of the earth, its potential energy is minus capital G, capital M, small m upon capital R plus small h. Here, the capital M and capital R are the earth mass and radius respectively. The next topic is escape velocity. We have seen that when a ball is thrown towards its velocity decreases because of the gravitation of the earth. The velocity becomes 0 after reaching a certain height, and after that the stone starts falling down. Its maximum height depends on its initial velocity. According to the Newton's third equation of motion is small v square is equal to small u square plus 2as. See the equation in a pictures. Small v is equal to the final velocity of the ball is equal to 0 and the acceleration a is equal to small negative g. Therefore, putting the value of v square is 0 is equal to small u square plus 2 in bracket a values minus g bracket close s as it is and maximum height of the ball small s is equal to minus u square upon 2g. Thus, higher the initial velocity u, the larger is the height reached by the ball. The reason for that is that the height here the initial velocity, the ball will oppose the gravity of the earth more and larger will be the height to which it can reach. We have seen above that the value of the small g keeps decreasing as we go higher above the surface of the earth. Thus, the force pulling the ball downward decreases as the ball goes up. If we keep increasing the initial velocity of the object, it will reach larger and larger heights and above a particular value of initial velocity of the ball. The ball is able to overcome the downward pull of the earth and can escape the earth forever and will not fall back on the earth. This velocity is called escape velocity. We can determine its value by using the law of conservation of energy as follows. An object going vertically upwards from the surface of the earth having an initial velocity equal to the escape velocity escapes the gravitational force of the earth. The force of gravity being inversely proportional to the square of the distance becomes 0 at infinite distance from the earth. This means that for the object to be free from gravity of the earth, it has to reach infinite distance from the earth. That is, the object will come to rest at an infinite distance and will stay there. For an object of a mass, see in a picture on the surface of the earth, kinetic energy is half mv square, while at an infinite distance from the earth, the kinetic energy is 0. The potential energy on the surface of the earth is minus capital G capital M small m upon capital R, while potential energy at an infinite distance from the earth is equal to minus G capital M upon M upon infinity is 0. The total energy of an object of mass m on the surface of earth, capital E is equal to kinetic energy plus potential energy, that is half mv square escape minus capital G capital M small m upon capital R, while the total energy for an object of the mass m at an infinite distance from the earth, E2 is equal to kinetic energy plus potential energy is 0. There is some solved examples are given in this book. You can see in your soft copy or the hard copy books. In a box, do you know weightlessness in a space? Space traveler as well as the object in the spacecraft appear to be floating. Why does this happen? Though the spacecraft is at a height from the surface of the earth, the value of small g there is not 0. In the space station, the value of the small g is only 11% less than its value on the surface of the earth. Thus, the height of a spacecraft is not the reason for their weightlessness. The weightlessness is caused by their being in the state of free fall. Though the spacecraft is not falling on the Earth because of its velocity along the orbit, the only force acting on it is a gravitational force on the Earth, and therefore it is in a free fall. As the velocity of the free fall does not depend on the properties of an object, the velocity of the free fall is the same for the spacecraft. The traveler and the object in the craft. Thus, if a traveler releases an object from her hand, it will remain stationary with respect to her and will appear to be weightlessness. Box closed. Dear friends, thanks for listening. These are the self-explanatory podcasts from Leader IAS and Yashas Institute. My name is Professor Suhas Sargar. Thanks for listening.